Corentin will start with advanced data containers.
Yep. So again, I'm just like repeating what I just said, but names substantial modification this morning before coming. Yeah. Well, anyway. So yesterday we did talk about fields. I'm not gonna repeat what I said yesterday, as well as data containers. So today I want to go one level deeper, explain some stuff that, for example, Chris has showed, and also like illustrate a bit more advanced ways of collecting your data and interacting with it. There are also a fun few examples. So today I want to talk about field parameters. It actually pertains to data containers, Boolean operations, cut regions, slices, and covering grids, which are different ways of querying your data and getting access to the underlying values on these CorDRF fields. Okay, so hopefully this code should be relatively clear. Let me just load a data set that I have on my hard drive. It need not be this one, but I'm using output 239, which is a Ramsys data set. It's nice. It has a nice galaxy in it. And also there should be online like a file called hello quantities.txt, which contains a position and a center. So if you want to use the data set that I'm using, you should download that txt file so that you actually know where the galaxy is, because otherwise it's a bit a needle in a haystack situation. Otherwise, I mean, do you all have a data set you can work with? Is that fine? Or who has a data set?
You should have.
Yeah, we should have. And is there anyone who does not have a data set that works? That's no. Anyway, so just to show you quickly, so here what I did is I loaded the data set. I got some center and radius from some text file that I generated a while ago. And then I created a sphere 4 times the Vera radius, so that is nicely centered on my galaxy. And if I run this on there you go. We have a nice looking galaxy. Yeah. Just yeah, so we have a nice galaxy. And so this morning session is going to be about cutting that galaxy into many different small pieces and trying to query different regions of the galaxy and so on and so forth. So it's centered on galaxies because this is what I'm doing, but it should be generic. Okay. And so if you've been following yesterday, we should have heard about like spheres, about regions. And so in principle, you should be able to do this, which is selecting a nice pencil-looking galaxy or like a pencil in your data set. So just out of curiosity, well, not out of curiosity, but like how would you select such a region?
Round.
It's not round. It's a rectangle, but because I have like created data, it looks a bit like fuzzy. Yeah, it's either a box or a cylinder. You can't see because that's well,
What's my question? Is it a box or cylinder?
yeah, no, it's a box, but it could have been a cylinder. Yeah. So in principle, in YT you have a ds.region, which gives you exactly a way of selecting that. So I can just illustrate it, and then afterwards we'll have a bit more time to actually do it. So if I do ds.region, I'm just like putting the signature again. We provide a center, a left edge, and a right edge. So I already had a center for my left edge. Sorry. Demo is always a bit hard. So I provide a center. For my left edge, I provide center minus, because I'm cutting in the y direction. So it's going to be some thickness in the x direction, some thickness in the y direction. Plus. and some height in the z direction. So I'm going to cut between some fraction of the real radius and so let's say minus your radius, and the right edge is going to be, oops. Down here. Is it not happy? And right edge is going to be center plus, this is a plus, this becomes a plus, and this becomes a plus. So hopefully it should select between the center and 10% of the zero radius in the x and y direction, and plus or minus zero radius in the z direction. And so if I do this, I get a region. Let's call it a region. And so if I do a projection plot and I pass in I region as my data source, hopefully it should work. Very good. So yeah, like nothing crazy. It just to refresh your memory from yesterday. Okay, but before I go into more advanced data container, I just want to ask you a couple of questions. So let's imagine that I create a sphere with these parameters. It's not a tricky question, but like, what do you expect the center of that sphere to be? Here. Sorry?
The same as before.
Yep, it should be exactly center. And the reason why is because, well, you have a sphere, and a sphere has a natural center, and you define your sphere with that center. When I created the region above, you created the region with a center as well, so like naturally you get a center. Now let's imagine that I have two spheres and I join them together with some Boolean operation. What should be the center? You in between? What if? Sorry?
Sorry, I don't get what do you mean? What is the center
Well,
that you define?
let's imagine that I have a way of joining two spheres by creating a data container that's the two spheres. What do you think should be the center, if anything?
I mean, centers are poorly defined by regular regions, right? This is the problem.
Yes, exactly. So the reason, so essentially YT does not make assumptions about your data sets unless it's like clear and unambiguous. So if you have two spheres, or if you have a region for which it's not clear what a center should be, then the center is not going to be defined. And the reason why it matters is because YT actually defines, has some derived fields that depends on, for example, the center. One such example is cylindrical theta and spherical radii, which are just in cylindrical and spherical coordinates, the position of your cells. So if I just create my sphere, I make a slice plot of theta in the x direction and in the y direction, the z direction, sorry. Well, it needs to read in data. Okay, so you get a value that's between, this is minus pi, this is plus pi, and this is 0. But because I'm slicing perpendicular to the, let's look at this one. So essentially I'm, by default, spherical coordinates and cylindrical coordinates assume that the z direction, this is the typical convention, but z direction is the vertical direction. So essentially your cylindrical theta is defined with respect to that z direction, and so you get this nice looking, well, this sort of like gradient looking thing. That's because, well, by convention everywhere in physics, vertical is usually the z direction. Turns out you can control that with field parameters. So if I have my sphere, I do field parameters, you see that there's a bunch of things defined. So there's the center, which is the thing that we talked about just before. Literally the center that I passed when I created the sphere. We also have a normal. So the normal is telling you what is up. And so by default, it's pointing to the z direction, Cartesian direction. I have no idea what it would be in cylindrical coordinates, but I would assume that it's actually direction. I would assume so. And then you get a radius as well, which is just the size of your sphere. If you have something that has a radius, then you get a radius. And you can also change these things. So if I create a new sphere and I set the normal to be pointing in the x direction instead of y, instead of z, sorry. And then I do slice plots. So now I get cylindrical theta, but this time it's revolving around the x-axis. So is that clear? Or so essentially I change the direction of the normal and know like some of the fields, including spherical and cylindrical fields, are defined with respect to that new convention. Similarly, you saw that there was a velocity, bulk velocity. So if you define, for example, relative velocities in a data region, then essentially it's going to be defined with respect to that bulk velocity. So it's going to be subtracted. All right. Yeah, and you can also define your own field parameters. For example, let's imagine that I define a mean density. I have a field that just returns it's a stupid example, but it just returns some mean value in the region. So it's going to pull the field parameter from your data container and then returns 1 times the mean density. So it's just going to be 1. Do it. I get a new field that's called gas mean density. And if I create a sphere and I pass in the field parameters like that, I'm going to create a sphere that has as an extra field parameter a mean density. If I do it, you can see that as expected, the gas mean density is now being equal to whatever you fed to the.
Not actually on camera.
I'm not on camera. Okay. And similarly, if I change the field parameter to set it to a different value, and I run that again, surprisingly, you get, well, you get out what you put in. So here it's a bit of a, well, this example is not super useful, but sometimes you have a data container and you want to define some quantity on that data container. And one good way of doing it to make it reusable for others is to use these field parameters. Right. Okay. So essentially, I just covered field parameters, which are ways of having your data container talk to your fields or your derived fields. Let's now see how we can build slightly more complicated data containers. And the first thing I want to talk about is Boolean data objects. So when you have containers, you can you can combine them using Boolean operations. And the separated operators are and, or, and not, and also XOR. I forgot to cover this one. So and is just if you have 2 regions and you do one and the other, that means that you're getting the intersection. If you have 2 regions and you do one, okay, I forgot some. I'm just going to change it because I realized this is not a complete list. So there's plus, there's minus. Okay, plus and or, there are minus, there's ands, and there's XOR, right? Mm-hmm. That's or.
I think the or needs to be a pipe, doesn't it?
Right. Yeah, sorry, it's just plus and sorry, it won't be or. See what you mean. So plus and pipe are actually the same thing. It's just Boolean or. So that if you have 2 data sets and you do 2 data container and you do one or the other, you do one plus the other, you're getting just the union of the 2. I'm going to an example. If you do one minus the other, you're getting, well, everything that's in the first but not in the second. And if you do one and the other, you're getting the intersection. If you do one XOR the other, you're getting the union minus the intersection. Let's try to exemplify that. I'm going to work on the circumgalactic medium. That's actually an example for Britain. So one way to define the circumgalactic medium is anything around a galaxy that's within some, let's say 2 times the radius of the galaxy, but that's outside of the disk, which is typically 10% of the galaxy. And so I can define my halo, so essentially the entirety of my galaxy, as being everything within 2 Vira radii. And the disk, it's a bit misleading because I use a sphere, but like the inner halo, that's for the sake of. So I define my inner halo as being anything within 10% of the radius. And then if I use this, I'm actually taking everything that's in the halo, but not in the inner halo. Okay. Look at that. Let's do a slice plot. So here I'm doing a slice plot using my data container. That's everything that's in the outer halo, but not in the inner halo. So if I do this, we're getting exactly what one was expecting. So you have everything up to 2 times the virial radius, but nothing within 10% of the virial radius. So I just cut out the center. If you do a projection plot, you're gonna see that, well, if you compare that to the plot I had at the very beginning, it's missing the galaxy at the center because I just removed it. But because you're doing a projection, there are things that is like front of the hole and behind the hole, so you're actually not seeing the hole when you do the projection, but if you do the slice, you can see neatly. Okay, so now I have a small exercise. We've seen up there how to do an eye. So let's try to take it to the next level. Instead of just being a boring vertical bar, let's try to create a plus. So maybe I can give you like, yeah, let's give you like 5 minutes and you try to reproduce that example here using data containers and Boolean objects. It's gonna get more interesting with the as we go along. So the end result is a smiley.
Starting a timer.
Okay, thank you. If you have any question, yeah. Yeah, so when you do slides, we're actually just looking at the central then do projection. That's essentially like a simple all input over. So like if you look at one side, just there's stuff ahead that you can't control.
Great selection.
Yeah, so I was with like a Russian of it. But we can like remove the cylinder from the street. And then maybe it's actual hole again. No focus. We sign
20 seconds.
Bit behind.
Yeah.
Trying to load the data, but there's a, basically is YT able to just load a whole folder of data at once sometimes, like it kind of is able to infer that there's this a collection of. So for example, I mean, can I show you?
Yeah.
Yes.
Um. So here I'm loading basically.
Yeah.
This one up at
Yeah,
239.
yeah.
That's a whole directory, right?
Yeah.
You pass a
Yeah.
stable.
Yeah, so YT is able to load, I mean, there are some data sets that are stored in entire folders. Ramses is one of them. The one you're pointing is actually Ramses.
Yeah.
And so it tries to guess what's in the folder. So if you provide a folder, it looks into the folder, and if it figure out that the only thing that can be in the folder is Ramses, then it happily loads it as Ramses. Or if it was another data set, then it would do it. It fails if there's any ambiguity.
Yeah.
So if you had a folder that contained both a Ramses dataset and some gadget snapshots, then you'd be like, I don't know what to do with that.
Pretty cool.
Yeah.
Thanks.
Yeah.
Thanks.
Okay, so did anyone succeed with the plus? Anyone succeed with like half a plus?
I heard it almost there.
Almost there. So should I do you need one more minute maybe, or? For those who've been struggling, I showed on the right here the script, the code to get this like high looking thing. In case that helps to create the plus. In the interest of time, I'm gonna move forward. There's a solution folder actually in the solution folder. So I noticed that a few of you managed to get this plus. How did you do it?
So the SPH data has a lot of like bumps around the edges.
Yep. So I guess this is so I'm not an expert in SPH, but my assumption would be that so whenever you do a region selection, you're getting everything for which the center. So if you have cells or particles, the particle position or the center of the cell needs to be in the region. But then
With SPH, it gets some of the neighbors. I thought it got all the neighbors, but maybe not.
it gets all the neighborhood.
I thought that it had I thought that it did a complete kernel for everything that was selected.
I thought it's like it's the particles within there plus its whole smoothing region.
Yeah, I think that's
Yeah.
what it is. So
Yeah. Yes, okay, so you get like a double wraps essentially. Yeah. This one. I mean, in the case of AMR, you can see also like some funky things at the side. All right. So yeah, so for those who had a plus, so what Boolean operation did you use, if any? Yeah, plus. Okay, it's a bit cheating. It's already written. But indeed, like if you take your hydrogen here, cheating a bit because I already wrote it, and then I have I can write a wide region. And see, instead of extending in the y direction, which is in the z direction, sorry, I want to extend it to the y direction. So this thing needs to be. So if I do. Okay. Just copy my projection plots. And I pass in this region. Hopefully. Yep. Is that clear for everybody why that works? So just for illustration, let's try, instead of doing plus, let's try to do minus. So essentially I'm taking the vertical thing and I'm removing the horizontal slab. And so what you get is that thing minus the intersection of the center. If I was to do it with and, that would be an intersection. So essentially I would get the intersection between the two, so just a small square at the center. And it. And if I do XOR, it's going to be thing that's in one but not two of these two regions. This I get a plus with a hole at the center. Really wide slow. Well, you should get a. While YT figures out what I'm trying to do, I'll move forward. Do you have any question for Booleans, or is that fine? Or yeah, I'll just kill it because I'm very impatient.
So the caret thing is, what is that, exclusive or?
This one.
Yeah.
So if it worked, which no, yeah, I think it does, but it might be very slow for. What the heck?
I get like a whole.
Yeah. Okay, no, it's slow for Ramses, and I'm if you were to run give blame, I would be to be blamed. So what it does is XOR. If you have a XOR B, then it's true only if A or B is true, but not if A and B are true. So in this case, that would be like the plus, and then the intersection at the middle would be removed. It's actually it's equivalent to writing the union of the two minus the intersection of the two. Which, also is going to be, so if you do the intersection, you get the square, and if you subtract that, you get the vector. Yeah, somehow it's faster. I don't know why. Well, I know why. I should have been a pull request, but that's yeah, Ramses. Anyway, so that's equivalent to the XOR, but for Ramses somehow it's slow. Let's move on. So that's ways of so if you have ways of selecting data in an interesting way, you can actually use this Boolean operation to construct more useful, but well, plus is not super useful apart for tutorials. But of course, you can define like a sphere, and then you subtract some region in the sphere that is not of interest, or you can build a slab and then you cut through the slab, or you can be creative about what you want to do. Essentially, anything you can draw on your on a piece of paper, in theory, you should be able to do it with YT. In this last word. If it's very complex, it might be tedious, but it should be possible. But sometimes geometry is not enough. Sometimes you want to cut on things that are not just spatial coordinates. And this is why there's cut regions. So cut regions, they give you a way of filtering your data objects based on what is in the data objects. So let's imagine that I still want to work on my circumgalactic medium. So let me just do a phase plot of the circumgalactic medium. So here on the x-axis, we have density. On the y-axis, we have temperature. Let's imagine that I'm interested in, I forgot, yeah. I'm interested in things that are relatively cold because I'm doing astronomy. Relatively cold is below 210⁴ Kelvin. That would be like anything that's in this phase diagram down there, plus like some things that are here. One way I can do it is to use the cut regions, or there are some shortcuts that are include above, include below, and include between, as well as exclude above, exclude below, and exclude between. That allow you to give a name of a field. In my case, let's say gas temperature, gas. So if I do my CGM selection, so that was the very reduced minus what is it at the center, dots include below, temperature 210⁴. Then I get all the cells that are in the region, but below 210⁴ in Kelvin. And I get a new data container, which is the beauty of it, like you always get its data containers all the way down. And if I plot the phase plot of that thing, unsurprisingly, well, you get only gas that's below 210⁴. What's quite nice is that now you've done a selection based on the value of a field, and you can also use it, for example, to do a projection. It works just fine. It looks funky, but this is only gas that's below 210⁴. And the reason why there's a hole here is because there's literally no gas here in the projection that's below 210⁴ within the virial radius. Blue seeing here is because you have cold gas outside of your radius. Well, anyway, that's this is where science starts, and this is where my talk stops. Potentially, let's imagine you want to do something a bit more fancy, and just including below or above some threshold is not enough. So let's go back just to our phase plot here. Let's imagine that I want only gas that's like on that side. You can't really, if you have a diagonal, you can't really express it as just it's below some temperature or above some density. It needs to be some combination of the two. Again, that's sort of a made up example, but just to illustrate my points. And one way of doing it is you can, like a diagonal, essentially, if you are here, then density divided by 10⁻⁴ whatever units, multiplied by temperature divided by 10⁴. Has to be larger than 1. So anyway, sorry. One way of doing a diagonal is to look at the ratio between your density and your temperature, and it needs to be larger than the ratio, for example, of here, 10⁻⁴ divided by 10⁴. That's one way of doing a diagonal, because you're looking at everything that's I don't know how to explain that properly. I don't think it made zero sense, did it? Did it make sense? No one. Can anyone?
I imagine if you asked, did it not make sense?
It did not make sense. People would have said yes, which is why I said it did not make sense.
Now they're not saying anything, so that means it did make sense.
Okay, well, what I'm trying to say is that if you're trying to do a cut in diagonal, I don't want to spend too much time here because that's just like a tangent, pun intended. But if you want to take a diagonal, essentially, whenever you're on the diagonal, if you go from being here to being there, for example, you multiply the density by a factor of 10, and you multiply the temperature by a factor of 10, which means that if you take the ratio, then that thing should always be larger than the same quantity. And so if you take ratio of density to temperature, it should be larger than some value. And that magical value is essentially where you're putting the intersection of that diagonal. Again, like this is just to do some slightly more complicated cut that can't be done with include below and include above. And so if I implement this, you can use cut regions. So cut regions are essentially doing the same thing as include above and below, but they give you full, you can write any Python, any string that would be interpreted by Python, and it will work. And it has a slightly funky syntax where you need to write obj, which is going to be your data container, and then you can use it as a regular data container. And it needs to return something that is Boolean, so it's either true or false for every cell in the data container. So for example, if I take the density and I divide it by the temperature, again, like this is my diagonal thing, it needs to be smaller than 10 to the minus 25, which is 10 to the minus 25 grams per cubic centimeter, divided by 10 to the 4, which is the threshold of my temperature. Well, anyway, if you can write algebraically like a way of cutting your thing or this function, then you can actually do it. And so if I do this, I get that beautiful, oops. Yeah, so where I cut out anything that's cold and dense, and I'm only left with things that are not cold, so warm and hot. Not cold and not dense. And so if I was to swap that thing here with a greater, then I would get the other side, so that I would get the other part of the diagonal. And the reason why it shifted because the x-axis have changed. Change the where? So it looks regular. All right. So essentially, no, I've covered cut regions, include above, include below. And I guess we try to have another short, what is it? Try to reproduce that plot here. So it's essentially a wedge. And I covered in the intro that you have a beautiful field called, where is it? Cylindrical theta. So essentially, you can build a wedge out of cutting on the value of theta, which allows you to do something a bit more complicated than there's no ds.wedge or ds.pi, or maybe we should do it pi as in like the thing you eat, not the thing you circle with. But with cut regions, you can actually do it. Maybe I can give you a couple of minutes to try to implement it. And so the name of the field you're probably interested in is cylindrical theta. And you can use ds, let me just write it. So ds that includes, sorry. Including sides, sp.cut region. Oh, and I forgot to mention that when you write sp.cut regions, you can actually provide multiple strings, and the cut is going to be wherever all of the strings evaluate to true. So if you write cylindrical theta is below some value, and then another, then you write cylindrical theta is larger than that value, is going to give you anything within the range. Speed up, right? Yeah. I'm realizing that I'm way behind in terms of where I thought I would be. No, it's okay. Well,
I don't know, I think this is really useful.
Why don't you just continue on?
doing what I'm doing.
Yeah.
Okay. And so if you just if some of you already have the wedge, there's a slightly more fun coding adventure going next. So you can also do a smiley using using a clever combination of a wedge and cutting on the radius and then Boolean operations. You can actually do it. There's the solution as well in the I think it's probably going to make it for next paper. That would be quite nice.
I like that.
Yeah. So if you're bored, just do or you can also do, I don't know, the Eye of Sauron or Beaker.
Oh, yeah, it's because coverage is a function. Oh, sorry, yeah.
No, it's the conclusion and this. You go to a. I just saw something like that. So I mean, you can achieve exactly the same thing with particle filters.
Okay. But it's a different design to for poly.
There's different syntax, yes.
It's a sign for
yeah.
that. I like to cut that a little bit.
Yeah, I didn't know that.
Interesting.
Yeah.
And is it possible to like, well, I guess yeah, it's
40
possible,
but
but just a specific set of particle lightnings or something.
Yeah, so particle filter is looks a bit the same as when you're doing derived fields.
Yeah.
Except it would be intermediate, and then you get a new function of particles that are reduced by that. So the function can be whatever. So if you have a list of IDs, you can just use that list. Yeah, I think that's.
Great, for YT. Right, I'm having a couple of issues. One is it doesn't have a cooling table. in its installation, so it can't actually compute temperature, right? So it's faking that.
What kind of data?
Well, it's the Ramsey's data.
Okay. Corentin, is special data needed to get the temperature field for the bucks that you have?
Through an error saying it doesn't have the temperature tables.
Oh, it's warning them.
Yeah, well,
It's
fake it
not
just shows a different, just fixed.
Yeah, so
Okay.
yeah, but it's only
Wait,
warning.
wait,
It's not the single
Oh, wait,
error.
Wait. But then it's throwing a more fatal error.
Yeah.
Which is, yeah, it says the unit quantities. That's numeric, says something, this has gone wrong. It's one thing. It's command. Well, you had set X unit and then it didn't like that.
You wrote xlim.
I changed it because it didn't like the other one.
Yeah, but xlim is expecting values between
Right,
two to cut.
so X unit or YT?
It's
Like the command one. Like
X unit.
That's something.
No X.
X. There was an X before. Yeah, then I saw you did XLim, so I changed it.
This is orange. Cool.
Oh,
I think we just have it.
Yeah.
it's, the kernel died.
The kernel died, yeah.
Yeah, it's getting lens.
Are you wedging or not wedging?
I'm doing something, but I don't think I'm doing it right, so
That's fine.
yeah. That's kind of what I'm working with, but I didn't include the commands I think that you wrote out on the screen. I think there might be more to this that I'm not adding.
Yeah. So along which axis is defined theta, and along which axis are you projecting?
Yeah, I probably didn't account for that, so,
Yeah.
yeah.
So I mean, by default, theta is defined with respect to z, and you're projecting along x. So essentially,
so I am.
Yeah. Yeah.
Oh,
so,
cool.
Yeah. So if you were to, it would probably look slightly better. Probably not super useful though. Yeah. Yeah, and the issue with, I guess, is your. That's interesting.
Thing to do, it's just kind of control the angle somehow, so
Yeah,
I'm
yeah.
guessing it's in radians.
Yeah, it's in radian. Yeah. Trace your lines and what was it again?
You wanna try 0?
Why not?
Okay, good.
So I mean, the syntax largely looks okay. Okay, that's encouraging.
Doesn't work. Oh. Is your SPC? Oh, wait.
Mhm.
Let's try this SPC CGM. And instead of a wedge. I'm just curious. I'll just mention.
Yeah.
And then okay. So one of your colleague had a very funny result. If you're unlucky and you or unlucky or a bit impatient in my case, and you stop YT as it's reading data, it will sometimes not realize that it's not done reading the data. Which means that when you then try to plot it, it's going to show you whatever it has read so far to the point where you stopped. And so in your case, when he was trying to hit just like a small corner because only a small subset got read and then something crashed. Yeah. Yeah. So this is the entirety of his simulation, according to YT. The way to get out of that, it's a bit annoying, but you have to recreate your data container. So that happens to me when I'm impatient and scripting. It should not happen when you're writing like an actual, sorry, not like when I'm doing like, for example, Jupyter notebooks. That's a typical gotcha. So I'm going to like provide some sort. The solutions are in the solution folder, but so you can actually do this with. I'll just show the solution and not run it because okay. So for the oh, I don't have the wedge, but the wedge is here actually. So you can cut on spherical theta. In my case, I cut between 2 pi over 3 and 5 pi over 3, which gives you a nice smiley. One thing I did not cover, but it's in the manual, you can provide some variables that are going to be evaluated when you write your the strings. So here I'm just telling it that NP is actually numpy with the locals parameter. Just a slightly because I didn't want to write 3.14 instead of 5. And then to make the smiley, well, actually, I'm just gonna paste it. Well, I created a wedge, which is the first example, and then I created a shell that's for the smile here. And then the smile is the intersection between the shell and the wedge, and that gives you a wedge and a shell that's a smile. And then the left eye and right eye are just the pencils from the beginning. And then the final smiley is the smile plus the eye, and then I took my sphere and then I subtracted whatever is in the smiley, which I very cleverly called dope. And then I do a slice plots of that selection. And if I do it, eventually I get slow, but actual smile. Wait. Yeah, there you go. Okay, so I mean, this was just for illustrative purposes, but essentially you can build whatever you want. And I'm going to just show the rest, and then we'll move on to the next. So other things you can do with data containers is creating ISO surfaces. So they're just ISO contours. So I can't run it because it's gonna take a couple of minutes, I think, on my
Go
go.
for it. I think what we'll do is you take us to coffee.
Yep.
And then I will go after coffee.
So you can create a surface object. So in my case, I'm creating a surface based on isocontours of 1 atoms per cubic centimeter. You get a data container that's behaving just as usual. So you can write data temperature, for example. It's going to take a little bit of time just because it needs to compute the isocontours, which is a costly operation. But then you will get, again, like a collection of all the points that are following. Yeah, there you go. You get all the points that are close to being at the isosurface of 1 atoms per cubic centimeter. And you can also make a... Yeah, somehow the phase plots don't work with surfaces, so we can't do phase plot, but you can do it manually. And so here I'm showing the phase plot of gas density versus temperature, and of metallicity versus temperature, because why not?
You have control over how close that has to be to the surface level, you said.
I don't remember how it's done. I actually don't know how it's done. So it's possible to, you know, Matt, or
You can't bracket a fixed region.
not exactly. So you can actually see it here on the left. Let me just close that.
Or it could interpolate.
Yeah, so you can see it on the left. I asked for an isocontour at 1 atoms per cubic centimeter, which should be here. You see that you get some scatter around it just because there's no...
That's the selected region.
Yeah, I mean, the thing is that you get the cells that are at the intersection. But you're not getting the intersection per se. You don't get the interpolation, I think.
Are you getting the cell on either side of the contour?
I don't know.
Oh.
It's hopefully in the doc, but I'm not sure. I think you're only getting... Yeah, I don't know.
Okay.
And that data container also has a nice dot triangles, which allows you to do ISO. You can plot like the thing in 3D. Again, like this is literally copy and pasted from the documentation, so it's just for illustrative purposes. But you can use matplotlib to actually display that. Again, it's gonna take a bit of time because it's slow, but you should see a nice 3D galaxy popping out once it's done. So this surface thing is quite useful if you're looking at all the structure of your data, or if you're trying to represent it in a slightly fancy way. That's one way of doing it. Without having to recode it manually, which is really tedious. Anything? Yeah.
So,
There it is.
There you
Oh,
so yeah, is this just plotting surfaces? So
It's the ISO contours, and here it's color coded by the temperature.
So presumably if you were able to, because I think Matplotlib can do some things where you like interactive, like, you know, spin it around and kind of
Yeah.
inspect it. So it'd be quite quick, right? Because it's not all the particles.
Yeah. So you should be, yeah, if you were using like a interactive rendering, you could like move around. It would be slow because yeah, there are still quite a lot of triangles.
Oh, okay.
I don't know how many there are, but
Oh, yeah, I see them. Yeah, there's a lot.
yeah, there's like 80,000 triangles, and Matplotlib is not super fast at doing it. In principle, you should be able to render it. So yeah, I mean, it's quite cool. Fun fact, you can actually provide that to a 3D printer and actually print a galaxy, which I did. It's super hard to do because the 3D printer is not meant for printing galaxies, but you can do it. You can also provide it and like print Lego tiles, but okay. And the final thing I wanted to cover is slices, cuts, and projections, which so a slice is literally you have your data and you just like cut it through, and the only thing you get is like the 2D intersection of whatever you had with your slice. And so you provide a direction, for example, here X, position along that direction. So in my case, for example, the center of my galaxy, which data source you're cutting from. It's optional, but it's useful. And then you provide some center so that it knows where the center is. This is sort of equivalent to that syntax that Matt likes, which would be ds.r, and then you provide a center and then colon on the 2 other dimensions, and that will give you a slice passing through that center. I'm not doing it because it actually works on the whole data set instead of and so it's super slow in my case. And so you get a slice. Again, like you can query the density and the temperature in the slice, and you get like flat 1D arrays because you get all the cells that are intersecting. You're not getting in actual projections. And you can compute the smallest cell in that slice and the largest cell in that slice. Similarities, if you want to do a slice but not along the Cartesian axis, you can do ds.cutting, and you provide a normal vector. So in which direction the thing that's perpendicular to your plane and the one point on the plane, and again, which data source you're coming from. And so if you do this, again, like you get exactly, so the beauty of YT is that you always get data containers that return exactly the same thing. So you can write all of your functions that just take in some data container that you don't need to specify what kind of data container, and that will always work, which I'm very happy about. And the last thing you can do is projection. So sometimes you want to flatten everything from like 3D structure onto 2D. And so you can use projections for that. Same syntax again, you provide a, so you provide, in this case, you provide a field because that's, you want to interpolate that field. You provide a direction in which you want to integrate, or in which you want to project, sorry. And you don't need to specify a point because you know you're like projecting the entirety of the thing, so there's no point anymore. And you can do it as well with some weighting. So each cell, instead of just summing, you can also like do a weighted sum. You can also compute the standard deviation. So if you pass moment is equal to 2, you will get the standard deviation of gas density integrated along the x direction weighted by the x, so by the size of the cell. Or you can also get the maximum value if you pass method is equal to max. Yeah, it's quite neat as well. And again, like you get a 1D flat array, you're not getting a projection. You're not getting like a 2D fixed resolution buffer, because fixed resolution buffer is my last thing I want to talk about, where sometimes you want to actually project onto 2D grids. And so you can use a fixed resolution buffer for that. One syntax is using this ds.r, where you can provide like a so here what I do is a slice where I want to slice and then get a 2D representation of my data through that slice. I provide a position, a left, a right, and then how many pixels I want on that side, and how many pixels I want on the z direction. And if I do this, then I get this time a 2D array that I can represent with matplotlib, which is just going through the galaxy. It's weird Python syntax. I never knew why, but like when you do when you're doing like NumPy indexing and you do A colon B colon and then you want some number, you need to write a J. I don't know why.
So J is how they indicate complex numbers.
Yeah.
And so we're hijacking the J here to indicate something different than if we had just left 1024. If we left 1024, that'd be a step size. If we do J, that's number of steps.
Yeah, okay.
And so NumPy does the same thing with mgrid, for instance. And so we just utilized the NumPy convention, which itself is not great.
I can let you look at that thing. Essentially, it's just like doing a slice projection, weighted projection, standard deviation projection, and max projection, and just to see the differences. But the final thing I want to mention is grids, arbitrary grids. So essentially, fixed resolution buffer are a way of going from 3D to a uniform 2D grid. You can also go from your 3D unstructured data set onto a regular 3D array using either this ds.r, where specify a left side, right side, and then number of pixels times j in both x, y, and z direction, and that would give me a 3D NumPy array or unit array that is 256 pixels on each of the 3 sides. Or I can also define ds.arbitrary grids, providing a left side, right side, and number of pixels. And so if I do this, then grid gas density is no longer a 1D array. This time it's a 3D array, like full 3D, which I can also plot. Well, I can't plot it directly, but I can, for example, sum it along one of the axes, represent it with matplotlib, and I get, well, again, the same thing. Arbitrary grid is super powerful, but it's a bit Well, if you already have a grid because you're working with gridded data sets, then you can actually use a covering grid, which is doing something similar than arbitrary grid, except it aligns itself with the AMR grid. So it's a bit faster and it's a bit more robust, I guess. And so you have two options. It's either covering grids or smooth covering grids. The syntax, I always forget. I copied it from, so like the first thing is how many refinement with respect to the minimum level of refinement of your simulation. And then you provide a left edge and then a dimension compared to that left edge at the current resolution. So I always get it wrong in terms of like how many, these numbers I always have to play with. The good thing is that then you still get a grid that's, you may have noticed it was faster, that's 256 cube. If I just show the images, the difference between covering grid and smooth covering grid is, can you see you can't see the difference. If you run it on your laptop, you should see that the smooth covering grid is smooth. While the non-smooth covering grid is not smooth. So the smooth covering grid, whenever you go from one level to the next one, you interpolate. And so you get something that's smoothed at the resolution of whatever you're trying to project onto. Cool. Yeah. And you can also do streamlines, but it doesn't work for Octs, so I can't show you anyway. And with that, I'm going to, I'm sorry for sorry for running late. That was a lot to cover.
That was a great one. Thank you.
Okay.
All right, I think we'll take a coffee break now and we'll return at 11:30 for the last two of the morning session. Yeah. So, yes.